Our guest speaker tonight is Dr. Phil Evans. Phil is an X-ray astronomer based at the University of Leicester and is involved with the Neil, how do you say it?
Gehrels.
That's it. The word that you said. Swift Observatory. He has designed and built unique software tools to allow observers to accurately analyze X-ray data from Swift. His primary area of research is transient astrophysical events. Following the retirement of Professor Osborne, he took on the leadership of Leicester Swift team in 2021. Further projects for Phil include the ESA's mission Athena, which will be launched in 2034. His talk this evening is entitled Confessions of an X-ray Pyromaniac, aka Studying the Transient High Energy Universe with the Neil, what he said, Swift Observatory. Please give a warm welcome to Dr. Phil Evans.
Very much.
Speech.
You can have a speech, which let me just zero the timer so I know how I'm doing. Well, thank you. It's a genuine pleasure to be here. I haven't given an in-person talk since pre-COVID. I have given talks last year, but for various reasons ended up being online. So it's actually a real, I enjoy talking about my work. It's good to tell taxpayers what they're paying for, but I also actually do enjoy meeting people. So it's great to be able to be here to have a chat with you. So you've already heard my title. I like to go for something that's just got a little bit of a pizzazz to it. And I am a bit of an X-ray pyromaniac because I study massive explosions. But yes, the scholarly title, if you like, is just more boring. So this is the Neil Gehrels Swift Observatory, which you'll hear more about in a few minutes. Let me, yes, keep half an eye on that.
The lights.
Oh, yes, the lights. Well done. Thank you. That works much better. Have to remember everything. The Neil Gehrels, right, so I should warn you from the start. I mean, as you'll hear a bit of, Swift, as we call it for short, has done a lot. This is not an exhaustive history of Swift or an exhaustive history of any area of particular science, because I was asked to keep it to an hour, not a month. And it's going to be quite biased towards the things that I'm interested in and indeed involved in, but that means I know what I'm talking about. So let's go straight in with what Swift is. This is Swift on the left here, and indeed this is Neil Gehrels. And this is Neil pre-launch. Obviously, Swift is in the clean room at NASA Goddard Space Flight Center, getting ready for launch. So it gives you an idea of scale. Neil was probably about the same height as me. And what Swift was designed to do is study gamma ray bursts. So this is, whereas that's a photo, this is an artist's impression of a gamma ray burst being studied by Swift. And really, to get started to explain what Swift is all about, I need to explain a little, very compressed, potted history of gamma ray bursts, and why Swift came about, and some of its particular features, which are really all driven by the science. So gamma ray burst story starts in the 1960s, and it starts in the Cold War. The Cold War crops up a few times in here. So for those of you like me who weren't around in the 1960s, it's worth a quick recap. Nuclear weapons are not good things, and setting them off all the time tends to be a bad idea. And so the USSR, as was then, and the USA and the UK agreed a test ban treaty that would stop setting nukes off with a test. And of course, each side had no confidence that the other one would actually obey it. And something is easy for us to forget now, because America got to the moon first, is that in the early 60s in particular, the Soviet Union were actually winning the space race. They were much ahead of where the US were. And there was this fear that the Soviets might stick a nuke on top of a rocket, fly it round the far side of the moon where you can't see it from Earth, and blow it up there as their test. So what the Americans did, and for their part the Russians did the same, was they built these satellites called Vela. This is obviously an artist's impression. And they were in pairs, and these could look for gamma radiation. And the idea is, if you blow up a nuke behind the moon, you get a big cloud of expanding material, which will eventually poke out from behind the moon, and will be radiating high energy gamma radiation. And Vela would be able to pick it up and spot the nuclear test. And I'm very, very pleased to be able to say that that never happened, and we're all still here today. But this guy here, that's me. This guy here, Ray Cleversardel, I'm sorry it's out of focus. I obviously didn't take the picture. Ray was one of the main software engineers on the Vela satellites. And he said, well, while we've got a gamma ray observatory up there looking for Russian nukes that aren't going off, I wonder if there's anything actually happening from the cosmos in terms of gamma rays, because no one had ever looked at that energy range before. And after many months of plowing through dot matrix printouts, he found this. So this is a light curve. Some of you will be familiar with light curves, I expect some might not. It's just a graph that shows brightness up here and time along there. So what we can see here is this gamma ray burst, what he saw, sorry, was no emission at all, and then a sudden spike of gamma rays that got very bright for about 1 second and turned off again, followed by another pulse that lasted about 8 seconds. And this is now known as the first gamma ray burst. This is a fantastic field to be in because unlike lots of areas of astronomy where you have things like planetary nebula that are nothing to do with planets, or early and late type galaxies that are completely misnomers, almost everything in this field is what it says. Gamma ray bursts are, guess what? Bursts of gamma rays. It's fantastic. It gets better. So actually, Ray originally called this a gamma burst. He took his own name out of the title, which we all find quite amusing. And this is now known as GRB 670702. And what that means is that the gamma rays reached Earth on 1967, July the 2nd. It is July. Yes, I can remember the months of the year. And the problem we have here, right, is this is it. That is the sum total of all the data that there were, right? And it turns out if you give theorists almost no information, they can do almost anything they want because there's no constraints. So, okay, Ray found a handful more of these, but for the next 20 years, there was almost no observational data, no progress in terms of getting data on gamma ray bursts, which meant that all sorts of ideas could be come up with. And there's this rather wonderful little paper that was written in 1994. So what's that, 27 years later, 27 years later, which listed in it 100 different models for what gamma ray bursts are that have been published in the scientific literature. I was taught as an undergraduate, if you're an observational astronomer, your job is to make life difficult for theorists. And so we do that, right, by getting better data. So this is Compton. Some of you may well have heard of Compton. I remember it was launched in the 90s. I remember reading about it in Sky and Telescope at the time. So this was one of NASA's great observatories. It's a gamma ray observatory. Just for fun, this is an actual photograph. It was deployed by the shuttle. So this is the cargo bay of the shuttle just there. There's the deploying arm. There's the Earth in the background. You might notice it's round. I hope that's not a surprise to anyone here. But Compton had on it this instrument called BATSI. So 1, 2, 3, 4, and then there's another 4 on the bottom. And these are gamma ray detectors, and their job was to look for gamma ray bursts and try and solve the riddle of what they were. Now, we don't know where they come from. We've got literally no idea where gamma ray bursts came from. That's one of the big problems we had. So this can look between them at the whole sky, handy. And also between them, they can roughly, and I mean roughly, localize where they come to. When Compton finds a gamma ray burst or found a gamma ray burst, it could localize it to an area about 6 times the size of the full moon. So that's not very accurate. On the other hand, you know, it's gamma rays. It's not like it's just pointing a telescope at it. And Compton gave us 2 major results. Here's the first one. This is a sky map of the 2,500 and more gamma ray bursts it detected over its life. And what you can see is they're basically scattered uniformly over the sky. So all the people who thought that they were aurorae on Jupiter were wrong. People who thought they were solar were wrong. In fact, the people who thought they were coming from the disk of our galaxy were wrong. Nearly everyone was wrong, actually. You know, there were 100 different models. These have to be either from the halo of our galaxy, so fairly close, or from the distant universe. That's the only way you can get a uniform pattern like that. So that helped straight away that we've narrowed a lot of the models down. The other thing is that Compton detected, well, 2,704 gamma ray bursts with the same instruments, so we knew that we could take the same measurements with them. And this is another result Chris Carvalho found. So this is like a bar chart, a histogram, whatever you want to call it. It's just showing how long the gamma ray burst lasted for and how many there were. So you can see there appear to be 2 populations of gamma ray bursts, some that last between a few milliseconds and maybe 2 seconds, quite a lot in that sample, and then a bigger population that lasts 2 up to maybe 1,000 seconds. And you're never going to guess this, but we call these short gamma ray bursts and long gamma ray bursts. And some people have argued that there might be another class in the middle, but we'll ignore them because it's probably not true and it's too confusing. So that's incredibly helpful, but still doesn't get us very far. And the thing is, we're really good at optical astronomy. I think we take it for granted, right? A kid can go outside, a small child can go outside and tell the difference between the sun, the moon, and the stars, right? I mean, not all at the same time, but that's because we've been doing optical astronomy for like 4,000 or 5,000 years. We've been doing gamma ray astronomy for 20. So the fact that, you know, until recently we couldn't even tell the difference between the sun, the moon, and the stars is just the nature of how young we are. So wouldn't it be great if we could do optical astronomy with gamma ray bursts? That means we've got to find them more accurately. So enter Beppo-Sachs. Beppo-Sachs was built in the mid-90s. It's an Italian-Dutch satellite. And I really just want to draw your attention to this instrument here. It's got a few instruments, but this one's really awesome. It's called the wide-field camera, and it can locate gamma rays quite accurately. And it does it something like this, okay? I'm doing a shadow puppet, yeah? I hope you're familiar with these. And this is almost exactly how Beppo-Sachs works, because if you know the shape of my hand, which you can measure it, and you know the distance from my hand to the screen, and you measure the shape of my shadow, you can work out with a bit of complicated maths the direction the light must be coming from to make the shadow that shape. I mean, you can sit when I'm too close to get sort of angles properly. If I moved around, if we were a long way away, I'd be able to demonstrate a bit better. So the way Sachs work, this wide field camera, is it has a gamma ray detector, and then in front of it, it has a grid. And instead of having my hand making an alleged dog shape on it, it has a set of lead tiles scattered around it, okay? I think they were in a random pattern. It doesn't have to be. And so when a gamma ray burst goes off, the gamma rays shine on the detectors and illuminate it. But where the lead is, it masks it out. It makes a shadow, and you do an inverse two-dimensional Fourier transform, I believe, and you end up with a reasonably accurate position. So everything's obvious with hindsight, right? I think that's genius. Just, I don't know who invented that. Maybe I should look up sometime, but it's genius. Anyway, the upshot of this is that in 1997, Beppo-Sachs discovered a gamma ray burst. Now, there was a gamma ray instrument on board that just said this has happened. They had to get the data onto the ground, analyze all of the data by hand to find where it was. And now they can locate it to an accuracy of what we call 3 arc minutes. So for those of you not familiar, that's 3/60ths of a degree. So 60 minutes in a degree, 60 seconds in a minute. So that's about the size, instead of 6 full moons, that's about a pinhead held at arm's length. So we're getting on for, I wrote it down here, a factor of 30. Yes, a factor of 30 better than Compton. So what they were then able to do was say, okay, so we've detected the gamma ray burst, we've got a reasonably accurate position. Let's turn around and point the other instruments on Beppo-Sachs at it. And that took about 8 hours. But after 8 hours, they found this bright X-ray object, and we call this an afterglow. It's a glow, and it comes after the gamma ray burst. I told you I love this field, right? It was expected. There's this wonderful line in one of the review papers about gamma ray bursts, and it says you dump some huge amount of energy into the surrounding gas and dust around whatever's exploded. This shocks it. And I love that line. But it creates shocks, and we expect that. And so you get this heated up gas that's then glowing and fading away. So if you can do that, in principle, you can find optical afterglows as well. I believe there was an optical afterglow to this first one, GRB 970228, so February the 28th, 1997. Oh, look at that, Jill, I hadn't noticed that. What are we? That is exactly, someone help me out here, 26 years ago today. Oh, well, there you go. That's quite nice, isn't it? Oh, I feel good about that. So there you go, 26th anniversary of the first ever gamma ray burst afterglow. How about that? Well, anyway, that's really quite nice. This in its own was a starting point. It wasn't the ending point. It showed that it could be done. What then happened was we managed to get one where we got the optical position, and we could then measure its distance. And I'm not going to talk about how we do that today. You can ask me later if you want, but we measured the distance, and we found it was a few billion light years away. Right, so suddenly of those 100 explanations for gamma ray bursts, we've got one, for long gamma ray bursts at least, we've got one that now works. The only thing that we can see is that this must be connected with the death of a massive star. And we actually got real smoking gun evidence of that, again, thanks to Beppo-Sachs, and April the 25th of 1998, where a nearby gamma ray burst went off, and it was close enough that the optical afterglow, when it faded, we then saw a supernova turning on, and a supernova we know is connected with the death of a massive star. So what we believe happens now is that under certain circumstances, when a star big enough reaches the end of its life, the core will collapse to a black hole, a lot of the matter will fall in, and under the right conditions, you get a jet of material launched at the top and bottom of the star, moving close to the speed of light. And if that jet is pointed at Earth, we see a gamma ray burst. So this is great, and this is all good stuff, and well done, Beppo Sachs. But there's still a huge amount of questions unanswered at this stage in time, like what are short gamma ray bursts, for example? And are those jets actually, I mean, this is speculation, this is what we think, but what about the physics of these jets? What's really going on? How do you launch them? Can we study, if these are so bright, can we detect them from a long way away? And although we're now getting a bit better at localizing them, Beppo Sachs still only found a small number of these objects. I spoonerize things a lot accidentally. It's even worse when it's vows. I'd just like to apologize in advance. I spoonerized Crystal Palace accidentally the other day. That didn't go down well. Anyway, the thing is, we don't have many GRBs from Beppo Sachs, and we want more of them. We want more that we've got positions for. We want to get more data. And we also don't want to have to wait 8 hours every time to go and observe it, because it's faded quite a lot in those 8 hours. And that is where Swift came in, okay? So Swift was also built on military technology developed in the Cold War. So the satellite body was provided by one of the military contractors. It's now Northrop Grumman. It was General Dynamics they were called at the time. And Swift is awesome in a whole variety of ways. So it has this instrument here called the BAT. That's there to look for new gamma ray bursts, a bit like BATSI did. It's the same technology as the wide field camera on Beppo Sachs, so it's your shadow puppet. It can see about 1/6 of the sky. See, at this point, we knew from BATSI that there are about 2 gamma ray bursts a day detectable from Earth. So with a field of view of 1/6 of the sky, you expect to see roughly 1 every 3 days. That's about what you can see with one eye open. And it can locate these gamma ray bursts, again, like Sachs, so about an accuracy of a pinhead at arm's length. But where Swift suddenly becomes awesome is Swift does not need to send the data to the ground to find that it's got a gamma ray burst. The satellite computer, or the BAT computer, can work out for itself within a handful of seconds, I've seen a gamma ray burst, and it can work out for itself where that gamma ray burst is. The spacecraft also has a clever computer on it that knows it's got all the ephemerides. These are gives you how celestial bodies move. So it knows where the Earth is, it knows where the moon is, it knows where the sun is. So it can work out for itself whether and when it's safe to reorientate towards it. And Swift can move incredibly quickly. I think, don't hold me to this because someone will come out and tell me I'm wrong, but I'm pretty sure it's still the fastest rotating. I mean, it's 18 years old now, and I'm pretty sure it's still the fastest rotating, at least astronomical satellite in orbit. I wouldn't like to speak for what the military might have. So when Swift detects a gamma ray burst, the BAT realizes it's found it. It tells the satellite where it is. The satellite decides, is this safe to look at it? And if so, it will just wang around and start pointing at it, so that within 2 minutes, it can have these other telescopes I'll tell you about in a minute pointing at it. Not 8 hours now, 2 minutes. The first we know of it is not, oh, I found a gamma ray burst, please can I go and look? It's a text message saying, I am already looking at this new gamma ray burst I found. It will autonomously schedule when it can look at it. So that was massive. And then it brings on board these extra 2 instruments, you see. So the X-ray telescope, this is my thing, being an X-ray pyromaniac. I work on this, and the camera here was built at Leicester. I didn't help build it. I joined the team afterwards. So we have our field of view is not like 1/6 of the sky. It's but it's plenty big enough to ensure that you're looking at the gamma ray burst that BAT found. It focuses X-rays, so we get some reasonably good images. And actually, this is about 3 times 3 times better than expected at launch. Dr. Mike Goad and myself have produced some software to really improve the quality of positions you get from the X-ray telescope. So now we can locate gamma ray bursts to 1.4 arc seconds. So a second is a 60th of a 60th of a degree. So that's a pin at 150 meters away. So that's I mean, that's by no means a record for X-rays, but it's pretty good for a mission with this kind of budget. And then there's a UV optical telescope, which is a standard, it's a Ritchie-Chrétien design. So some of you keen astronomers here might have or have used Ritchie-Chrétien design telescopes. And it's got a filter wheel that goes through the UV and optical colors. And of course, being an optical telescope, it can be very accurate, right? It can locate things to half an arc second. And again, for reference, that's like a pinhead 400 meters away. So we're talking proper good accurate positions now. So what did Swift do? Let's go through. I'm going to start with a few highlight results from the gamma ray burst world, including some very breaking news. So This is not breaking news. This is from 2005. One of the questions is what a short gamma ray burst. We'd never found an afterglow of a short gamma ray burst until this one. I inexplicably not put the number down. I'm pretty sure this is 050509, so May the 5th, 2005. And it actually shows you quite well the problem. So it would have been really nice if they'd put this inset just over here, but I didn't make this image. So this is an optical image of the sky, and this red circle is what we call the bat error circle. So this is your pinhead at arm's length. So bat has said a GRB went off somewhere in that red circle, and you can see straight away there's just so much there. How could you ever know which one of those caused the GRB? And I think about, in the Batty days when this was 6 full moons big. The X-ray telescope, however, got an afterglow. Now, this was before Mike and I had improved the position. So this circle's probably about 3 times bigger than it would be nowadays, certainly twice as big. But it seems to suggest that the object that's gone gamma ray burst is in this elliptical galaxy. Now, that can't be the death of a massive star, because elliptical stars and elliptical galaxies are basically already dead. They don't go supernova. And actually, since this point, Swift has localized short GRBs to basically every type of galaxy there is. Long GRBs are always in star-forming galaxies where you get supernovae. And this is a very stylized movie. Okay, NASA made this. It's not scientific. It's kind of indicative. That's the word I'm looking for. But the idea of what we think there might cause short gamma ray bursts, and hold on to this thought because I'll come back to it in a few minutes, is we have here 2 neutron stars. So for those of you who don't know neutron stars, these are left behind by supernovae that didn't leave black holes behind. They're really, really dense, okay? A typical neutron star might have 2 or 3 times as much stuff in it as our sun does, crammed into a ball smaller than Nottingham. It's about 10 kilometers across. So that whole thing is about 10 kilometers, well, 10 kilometers in radius, so 20 kilometers left to right, with twice as much stuff in it as the sun. And if you get 2 of these very close together, they will eventually spiral into each other because of something that Einstein predicted in general relativity. They create ripples in space-time. And the idea is that as they do that, they will eventually tear themselves apart. The cores will collapse down to form a new black hole, and you will get this very stylized, but a little whoosh of jet of material at the end. And if that's pointed towards you, you will see a short gamma ray burst. At least that was the idea. And people have been muttering about that for a while, but it took Swift getting those very fast response to get the positions to actually be able to show that. Another problem we had, these are some more of these things I call light curves. So this is just the brightness, gamma ray burst fading with time, and there's a few different gamma ray bursts on here. This is the quality of data that we had before Swift, okay? And for those who can't see, this starts at about 20,000 seconds after the gamma ray burst. So the earliest we've seen, that's about 8 hours. But they all seem to just be decaying kind of like that. And there's a reason that people expect that from scientific theory, which is far too boring to go into in great detail. But basically, we expected them to be decaying like this. But we wanted to know what's actually happening. And we wanted to get some of the details about how they change as they decay, because it gives you some detailed physics of these jets. Yeah, well, the universe doesn't behave like we want. So Swift launched, and Swift started observing lots of gamma ray bursts at early times. And this model was produced because it seemed that a lot of them didn't look anything like that. And instead of just carrying on, what we thought, right, was the light curves would just have this line that would just continue back all the way back there. And instead, it's turned out they have this steep decay, and then they go flat, and then they go steep again. Or at least that's what we thought at first with Swift. So John Nosek, the Swift mission director at Penn State University in the US, he wrote this paper in 2006, and he called this the canonical afterglow. And he said, this is what gamma ray burst afterglows tend to look like now. And probably, if you don't see every part of this, it's just observing effects. You weren't looking at quite the right time. But we carried on gathering more data. I joined the Swift team shortly after this came out, actually, as part of the post-launch support team. I started on the 2nd of August, 2006. And the job that I was assigned first was, Phil, we've got this issue that when we detect new gamma ray bursts, Swift does all its stuff automatically, but then humans are having to analyze the data, and then they'll get more data, and they have to analyze that, and then we get more data, and they have to analyze that. And humans make mistakes, especially when it's 3:30 in the morning and you've just been woken up by a gamma ray burst. So I was given the task of trying to produce some software to automatically create light curves. And I think, I'm pretty sure this is still, it certainly was first, but I think it's still largely unique in the world for giving you fully analysed publication quality data. We've found that the stuff that we create using my tools is actually usually more reliable than you get by hand, which is nice. And computers don't care that it's 3 a.m. and they've just been woken up. So when I published that, all those details in 2009, by then we've got more than 300 gamma ray bursts seen by Swift. And what we found is actually this canonical light curve isn't canonical at all. About 40% of gamma ray bursts follow that pattern, but actually we've got some that just seem to go, steeper than shallow, some that look like we thought they were going to look before Swift came along, and some that almost do the opposite behavior. That one falls quickly and then flattens off. This one starts shallow and goes steep. And who knows what that one's doing? We have quite a few of these oddballs. So actually, there's a saying now in gamma ray burst science, which is when you've seen one GRB, you've seen one GRB. They're pretty unpredictable. But you can still get surprised. So that, I mean, I wrote that paper, however long, 2009 is ago, a scary amount of time ago, really. Now I'm going to bring you right up to date, and this is literally hot off the press, or in fact hot on the press, because this paper hasn't been published yet. So I have asked, this is why one of the two reasons I've asked this talk not to go on public social media yet. Our paper is actually available. But last year, while I was at a conference, things interesting often happen when I'm at conferences. I don't know why. I was at a conference in Germany on the 9th of October last year, and a gamma ray burst went off. And our first response was, wow, that's bright. And then we went, hang on a minute, this is the same gamma ray burst that a satellite called Fermi detected an hour ago. Why have we triggered on a gamma ray burst that went off an hour ago? BAT doesn't detect GRBs an hour old. And actually, BAT had detected the afterglow bright enough to make it think it was a new GRB. Now, that just doesn't happen, ever. Okay, and so we started observing it, and you had so many data points in here because it was so bright. Now, Swift, one of Swift's clever things is it has two observing modes for the X-ray telescope, because when something's really bright, essentially you can't read out the whole detector your normal way. You'd saturate, you'd lose a load of data. So I'll show you an image in a minute, but we squash the whole thing down into one dimension. And Swift automatically realizes when it's faint enough that we can go to the more normal mode. And normally we will be getting data in, it's colored blue in all of my plots. In this fast mode called window timing mode, we'll be getting data in window timing mode, typically for maybe 1,000 seconds for a bright GRB. Often we don't even go into window timing mode. We were getting data in window timing mode for 2 days with this GRB. I mean, it was ridiculous. We could not believe what was going on. This was just so amazingly bright. And just to make life more fun, one of my colleagues, and this is pretty impressive. So this is a typical image in window timing mode, right? It's all squashed down into one dimension. So all you see is this one strip of data. And my colleague looked at this and said, that doesn't look like a normal gamma ray burst to me. Yeah, Andy, I can clearly see what you mean. Not. But Andy said, no, I'm sure that we're seeing some effects of dust in this image. And so he said, can we I know it's too bright, but can we just take a quick image, please? And actually, as it happened, we took Andy's image, which is that red dot there. And then shortly afterwards, it got faint enough that we automatically went into imaging mode. And this is what we found, these fantastic images. Now, what we're seeing here is this is the gamma ray burst, or rather, this is the afterglow of the gamma ray burst. These are at different times. So 1 day, 1.5, 3 and 5.5 days. What's happening is the gamma ray burst has gone kaboom. Like, I've forgotten the exact distance of this, but it's a few billion light years. And the light's been traveling therefore for a few billion years. And some of the light is going straight along, and we've got to us. We saw the gamma ray burst, and now we're seeing the afterglow. But some of the light from the gamma ray burst, from the actual burst itself, the original explosion, was not going towards us. It was heading off over in that direction. But then it's got as far as our galaxy, and it's hit a big cloud of dust in our galaxy. And some of that light is scattered off the cloud of dust to come back down to us so that we see it. Of course, it looks like it's not coming from the gamma ray burst. It looks like it's coming from this dust cloud. And of course, that light's had to travel further because it's gone 2 sides of a triangle, so we see it later. So what we're actually seeing here, these really beautiful expanding rings, is actually we're seeing echo after echo after echo of the original explosion being scattered off different layers of dust within our galaxy. So just by studying this particular blast, we've learned about the existence and shape and even the molecular composition of this cloud of dust in our galaxy by looking at something, you know, in a remote galaxy a few billion light years away, which is really, really quite neat and awesome. I said that this was bright. Let me quantify that a bit more. This is so my tools, because I can analyze every gamma ray burst. I've got this big catalog, and this is the light curve of every gamma ray burst Swift has ever seen. They're kind of blurred out, and so the darker the color, the more gamma ray bursts there are at this time. This one here in orange, this is what used to be one of the brightest things we've seen. This alone is an awesome event. It was in 2008, and it was briefly, it was literally pretty much exactly halfway across the universe. And it peaked in optical at magnitude 5.3. And for those of you who are astronomers, you'll be nodding and going, hang on a minute, that's like naked eye brightness, right? So this is actually the brightest thing that there must be surely somewhere some human happened to see it accidentally. I mean, it would only been for a few seconds. They probably didn't realize it, but I'd love to think someone did. So we thought this was bright. And then in 2013, this thing came along, and we didn't get on it quick enough to see if it peaked in naked eye brightness. But in X-rays, it was even brighter. And, you know, 2210 just says, hold my beer. You know, at a few thousand seconds, we're talking nearly 100 times brighter than anything we've seen before. And this is not just like fun because it's bright, but it means we can get so much data that you can really challenge your understanding of what's going on. Now, the obvious question is, isn't that just, maybe it's just nearby, you know, things look brighter when they're near to you, right? Well, yes and no. This is, you can correct for distance. We don't have as many objects that we know the distance for. But when you correct for distance, you see that it's still not quite the brightest event ever seen, but still one of the brightest. So this is fantastic. This has been studied by basically every astronomer interested in transient astrophysics in the world. There will be, there's a special edition of the Astrophysical Journal being published at the end of March to coincide with a high energy astronomy meeting in the United States. And so they're going to have, our paper is in the public domain, but all of the papers are going to be published, and there'll be a big press splash at the end of March. So keep your eye out for that. I've actually been proofreading one of the, no, that's for something else. I've been helping write one of the press releases for this week. So keep an eye out for that. The other result I want to show you before I move on to more recent or to different stuff is not actually a gamma ray burst, but we thought it was. So Swift detected a gamma ray burst, we thought, and we started observing it. And then a minute later, BAT detected it again. BAT said it's exploded again. And then it said it's exploded again and again. And we stopped thinking, hang on a minute, gamma ray burst, you know, once a star's blown up, you can't blow it up again, can you? And no, you can't. And this turned out to be something rather exciting. This was the first ever what we called a relativistic tidal disruption event. So there was a nice movie that NASA made of this. So what's going on here? You've got a black hole here that's about 100 million times the mass of our sun, and a star has by accident got a little bit too close to it, and it starts to get shredded and pulled apart by the black hole. And we've seen that on a few occasions before, but in this case, it happened for whatever reason that this jet of material was also produced. And we were pointing that jet at us. It's a question how many of these events actually have jets is an open question. And this was the first time this behavior had ever been seen. We then found a few of them in fairly quick succession, which is one of the weird things the universe does sometimes. But this was also a nice result, but it's a segue into where we're going, because this is not a gamma ray burst, but Swift detected it, and it was a unique discovery by Swift anyway. Now, in this case, we detected it because we thought it was a gamma ray burst. But the general point is that Swift, because of the way it's designed, can do a lot more than just gamma ray burst science. It's a rapid response satellite. Most satellites don't move quickly, and most satellite operations teams don't move quickly either. They're going to love that if they find it on YouTube. I love you guys, honestly, but Swift is awesome. But actually, genuinely, the point is, so if you take something like Hubble or Chandra or whatever, these are fantastic observatories, but their MO is built around pre-planned observations. So they have once a year or twice a year a proposal around where people request observations, and they're scheduled weeks or even months in advance. Swift is built around discovering new things and responding to it. So we have literally every day, we had a telecon at 2 o'clock today where we planned what we were observing tomorrow. You know, we have to be flexible. We've got 3 instruments. We're happy to be interrupted. I'll say more about that in a second. And also all those tools that I made to analyze gamma ray burst data, actually, I've now made general. You can analyze any object seen by the Swift XRT. Usually learning to use a new instrument is a right pain in the backside. You've got manuals to read, you've got data to understand, you've got calibration to worry about, and you'll always make a mistake, and there's lots of little subtle gotchas, and it can take a long time to analyze your data. For the Swift X-ray telescope, you go to my website, you type in a few details of what products you want, and you click a button to go, and it does it all for you. and you get back publication quality data. So this also makes Swift very attractive. Now, even satellites that are built around pre-planned observations, you know, they're run by professional astronomers who are intelligent people, and they know the universe does weird stuff. So they have programs where you can submit what's called a target of opportunity. You can say, something has happened that's interesting. Please, will you arrange to interrupt whatever your plans were and look at my object for me? And they may say yes, or they may say no. And I don't have the numbers for this, but anecdotally, the big observatories do like a handful of these a year. And they take some time to interrupt. I mean, I asked Chandra to do one recently for me, and it needed sort of 3 days notice to be able to get the observation in. Swift does more than 1,000 of these a year at the moment. That's you know, I mean, just work it out. That's several a day. Swift is not an acronym. People often write it as an acronym. We say if it were an acronym, it would be swamped with infinite flipping TOOs, because we get an awful lot of them. And we can respond to them within, you know, minutes to hours of the TOO requests coming in. So Swift is actually able to do a lot more science and has really reinvented itself as not just a gamma ray burst observatory, but a general purpose observatory. Now, sadly, Neil Gehrels, who we saw standing next to Swift in the first slide, Neil passed away in 2016, fairly suddenly actually, to cancer. And in 2017, in acknowledgement of his legacy and his role in making Swift into this general purpose observatory, we were renamed the Neil Gehrels Swift Observatory in Neil's honor. So what science can we do with Swift that we don't do with, so there's not necessarily directly gamma ray bursts? Well, I'm going to start off with one, and it's a real pity Neil didn't see the fruit of this actually, because he was involved in planning this. Gravitational waves. I love gravitational waves. I have mass. I hope I'm not that massive, but I have mass. And while I'm walking around, I'm accelerating. And I know you don't realize this, but I'm making all of you like deform by doing so. Because I'm generating gravitational waves, and any accelerating mass creates gravitational waves, which are ripples in space-time. And so, you know, if this is the Earth, it's kind of wibbling like that as I move around. The good news is they're like really, really, really weak. So to detect gravitational waves is hard, but if you have something really massive, let's say 2 neutron stars, and they're really close together and accelerating very quickly, let's say spiraling in like we think short GRBs are, you might just get gravitational waves strong enough to detect. And we detect them through this ridiculously both simple and actually highly complicated technology. This is LIGO, okay? So you can see there's 2 tunnels. I'm going to be LIGO for you, okay? So stand well, I'm not getting too blinded. My arms are 4 kilometers long each. There's a mirror on the end of each of my little fingers, and there's a laser shining somewhere through my back, and it goes down both of these tunnels and comes back and recombines. And don't worry too much. For those of you who've studied microsync interferometers, this is a microsync interferometer just with some seriously awesome adaptations. But the point is, right, when a gravitational wave goes through the Earth, the arms will move like this. I'm exaggerating their movement, but they will move like this. And what that means is where the laser light rejoins, it's specially lined up so that you get destructive interference. This means you don't see any light at the output. But as you make the arms wobble, you get light will flash on and off at the output. So in 2015, that happened for the first time we detected it. This was not actually, this is going to show you how hard this is to do. These were not 2 neutron stars weighing twice the mass of the sun. These were 2 black holes weighing 30 times the mass of the sun coalescing, okay? And when I say these arms did this, what I mean is they went from being 4 kilometers long to being 4.00000000000000000000000000001 kilometers long. And for those of you who couldn't count, that was 21 zeros. That means that mirrors moved by less than a proton's width. And they measured it. I mean, how awesome are the people who invented that technology? You literally, right, you know, they have problems with, you know, they can detect cars, they detect earthquakes. I'm pretty sure when the person in the control room sneezes, it causes a wibble. And somehow they detected gravitational waves, which was awesome. Now, they're very difficult to follow up because they're hard to locate accurately. But after a lot of work in 2017, everything really paid off because LIGO and Virgo, the gravitational wave detectors, found 2 neutron stars coalescing, a signal from 2 neutron stars coalescing. And we were able to track the afterglow. We were able to find the optical light that came from it and link gravitational waves and optical light for the first time. I was involved in this one here, Vista, where these 6 teams independently discovered it. We didn't find any X-rays with Swift. Turned out because the X-rays didn't actually switch on for about a week. And then this is the Chandra image. They're so close. This is the galaxy that it was in. So you can see the host galaxy and the transient. In X-rays, Chandra can separate them. The resolving power Swift, our optics are just not good enough to split these. So we never actually managed to see it, unfortunately. But we did see it with the UV telescope. So this is a zoom in. You can see, you might recognize the name now. I got to write this up. So we discovered it and then it faded away. So a guy called Brad Senko sort of taken over from this now, but I led the program with Swift to try to identify the counterparts of these. So this was a very exciting moment for me. But what else can we do? So this is multi-messenger astronomy. It's a talk in itself, science without light. That's just a highlight. What else can we do? Here's another really awesome thing that happened with Swift this is going way back to 2008. And this looks, well, frankly, was really lucky. So Alicia Soderberg is using Swift and she's using the UV telescope, which I've not shown here, to study a supernova, which is somewhere down here off the bottom left. And she happened to look at the X-ray data, even though she wasn't using it. And what she found is one day she's looking at her supernova down here, and this is the X-ray field. And then the next day she's looking at the supernova down here, and suddenly there's something massive gone off in the X-ray telescope that's not here. Now, we don't have the X-ray telescope isn't our trigger instrument. It doesn't trigger like the bat does. So this was only found because Alicia happened to check the data and realized that something new had gone off. This turned out to be a supernova, so a second supernova in the same galaxy. And this was the first time we've seen the X-rays that you expect, theoretically had been predicted, that when the shockwave of a supernova first breaks out of the envelope of a star, you should get this burst of X-rays. And we found it almost completely by accident, which is, you know, really rather exciting. But it makes you wonder what else is there out there? You know, what if Alicia hadn't looked at these data? Would we have seen it? Is there other stuff kicking around there we haven't found? So we start to ask this question and we say, what can we do to try to make this a bit more systematic? So we have a program led by my colleague Jamie in the States, which is to look at the Small Magellanic Cloud. We have this pattern here overlooking the Small Magellanic Cloud. And we look at that basically every week. So we look for 60 seconds for each of, I think there's 267 fields in there, and we'll look at each of them for 60 seconds once a week, because we know there are certain types of transient events, certain types of eruptive stars in the SMC, in the Small Magellanic Cloud. That's one of our satellite galaxies. And so we want to see if we can spot them going off. And we found some really cool stuff, including we found star systems that from basic stellar theory ought to be impossible. So they tell us there's some really funky stellar evolution going on in there. So that's kind of neat. We've also had, I mentioned that tidal disruption event. You remember the star being ripped apart by a black hole with the jets? Well, we found a few of those in Swift data without the jets, or at least not jets that we have seen. But the problem with finding all of this kind of cool stuff is that either you have to be really lucky, like we were when Alicia looked at the data, or you have to know where to look, like when we look at the SMC, or you find things like this. And one of my colleagues recently finished his PhD using Swift data, and he was looking for things like this, but you're looking in old data. You're looking through and saying, hey, we've got all this old data. So Swift was looking at this object, but it could see lots else. I wonder what else it saw. So it means you're always, you know, either relying on luck or you're finding things years after they've happened. So X-ray catalogs are a very powerful tool for looking for these things that you weren't expecting to see, to finding what's hidden in the data. And I'll say a little bit more about this in a moment, but the XMM and Chandra are big X-ray observatories. And in their catalogs, people have searched back in the back catalogue of data and gone, oh, look, we found these objects. And some are known as QPEs, which are quasi-periodic eruptions, which you'll hear more about in a second. And some that are called fast X-ray transients. We don't know what these are, but we know that they're X-ray transients and they're fast. So that's why we gave them that name. This is the Swift catalogue. So Swift's got its own catalogue. I built this in 2014. This was the first one. So Swift covers quite a lot of the sky because it looks around very quickly. It's not as sensitive as some of these bigger instruments, but it's covered way more of the sky. So this first catalogue, we had about 150,000 objects, a bunch of which seem to be varying. I updated that a few years ago, and you can see it covers an awful lot more of the sky, and we've got about 50,000 extra objects in there. And actually, so I mentioned my colleague Rob, who say works for me now, but he was doing his PhD a year or two ago, and he basically looked through this catalogue trying to find these tidal disruption events, these stars being ripped apart in our historical data, and he found a handful. But the problem with this approach, right, is that it's always old. It's always out of date. I mean, I work pretty hard, and I'm rather proud of these catalogues, I've got to say, because when I told my boss that I was going to do this, the first one, he looked at me and he said, Phil, this took person decades for XMM to do this, and you've got you. Are you sure you haven't bitten off more than you can chew? Ha, well, no, I haven't. Feel a bit smug about that. Anyway, but the point is, it takes a long time, right? Because processing the data is slow. So we chose a point and we said we're going to stop with all the data in 2018 August. And at that point, I started processing the data, and you wait for it all to process, which takes ages. Then you go and check it and realize you made some mistakes, and you fix your code and you go and do it again, even though you were sure you'd bug fixed your code before you started, you know. And then you have to collate all the data, and then you have to make a web interface to make it available. Then you have to write the paper. And so it was not published until 10 months after it. So by the time this went into the public domain, it was already 10 months old. The XMM satellite has a much bigger team than me. But also much more data because they've got a bigger telescope. But even for them, their latest catalogue was 8 months old by the time it's published. So what that means is if you want to then go and look through, like people have, and say, have we got any interesting transient events in our data? Even if you find them and you can do great stuff, they're not really there for chasing up now, right? Because they're really old. But remember, Swift is fast. Swift is built around being flexible. Swift's now easy for us to analyze the XR data, and I have a bunch of tools that I've built to be my job. I have tools that run automatically whenever we get data. I have tools, I built the catalogs so they can find the sources. I have tools to analyze those sources. So I started to ask, and this was more than 7 years ago, I asked this question. It's been a long journey. It's about probably about 2015, I first started thinking this. Could I build something that can look for unexpected transients, what we call serendipitous ones, not what we're looking at, just stuff that happens to be in our field of view in close to real time? And to cut a long story short, the answer is yes, but it's really hard. First of all, how do you know if a source is really a transient? How many of you have looked at this night sky with binoculars? Yeah, most of you. Do you remember the first time you did it? And you're like, oh, wow, there's a lot more stars there than I realized. They hadn't just switched on. They weren't new transients that had just switched on. It's just you'd never looked with enough sensitivity before. So most of the sky has not been observed with the sensitive X-ray telescopes. If you point Swift at a bit of sky, you find a whole lot of sources that are new in this sense they've never been seen before. How do you know if they are actually new because they're transient or just new because, you know, you put your binoculars on the sky? And I've got to say, my first attempt at this in about 2015 came up with an awful lot of stuff that wasn't transient. The real question is, what do you use as your reference catalogue? You can take satellites that have surveyed the whole sky, but they weren't very sensitive. So you lose a lot of transients if that's your baseline. But I think actually, Swift spends a lot of time re-observing the same bit of sky over and over. We detect a gamma ray burst. We look at the small Magellanic Cloud, whatever. We look, and then we look again, and then we look again. And so this question starts coming, maybe we can build a catalogue. Can we build a catalogue from Swift in real time? It's not been done before to build a sensitive X-ray catalogue in real time. But if you could, you'd have your reference to tell if you found something new, you know, free of charge, wouldn't you? It's also paying, you know, Swift observes Swift has got it's like the ADHD child of the space industry, right? Something like Hubble, and I say this as someone who's himself hyperactive. Something like Hubble, right, is looking at an object that's over there and it's orbiting the Earth, and the Earth gets in the way, so Hubble will just switch off and I'll just wait, come on, have a snooze. Oh, good, it's come back out from behind the Earth. I'll look again. Swift will go, oh, what I was looking at's hidden. That's boring. Right, let's go and look over at that now. Oh, that's behind the Earth. Let's look over at that. You know, Swift is constantly bouncing around. Swift observes typically about 80 objects a day, which is about 40 times as many as most satellites might expect to do. And that means that I'm constantly getting new data. So if you want a catalogue, you've got to realize that it's changing all the smegging time. So what you do is you go away and you spend a very long time drawing flowcharts like this that don't actually achieve much except to convince you that this is really complicated. Anyone who's a proper software engineer, I'd like to apologize, especially like, I think, I can't read it from here, but something like that box is about, you know, 10 different pieces of software in one box, you know, and that's like one line of code. It's not a very uniform distribution. But anyway, it turns out that if you spend an awful lot of time drinking caffeinated drinks and saying increasingly bad and creative swear words, you end up with a living Swift XRT point source catalogue. And I think, at least I've claimed this is unique. I'm pretty sure this is at the moment the only sensitive X-ray catalogue that's actually updated in real time. So it's very exciting. So these are just a couple of characteristics of it. Obviously, some bits of the sky we've looked at loads. Some bits of the sky we've not looked at much. So you can see what this is showing is there's bits of the sky we've only looked at about 100 seconds, but we've covered about 5,000 square degrees of the sky at that. And then at the other end of the extreme, you've got the bits of the sky that we've observed for more than 2 million seconds, but there's not much of the sky. In fact, this is an image of the deepest field we've got. If you're interested, it is Swift J1644, that tidal disruption event I showed you. We've been observing that for ages. So this is a false color X-ray image of that field. So as of a week ago, these numbers are all out of date because this is updated like every 2 hours. But as of a week ago, we covered 5 and a bit thousand square degrees, and we've now got nearly 300,000 sources. But, and this is where it gets to be fun, you see, every time we get data down, you build a list of objects in that field, and then you go, are any of these new? And a lot of the time you can say, I don't know. What did I look at last time I looked at this field? And you can start to look for transients in real time, at least in theory. So this was published just earlier this year. Takes a while for things to go through the publication process. The code was first turned on in its test mode on April the 1st last year. I did realize that that was maybe not the most auspicious day to do it. And I said that things always happen when I'm at conferences, right? In June of last year, the Swift XRT team got together for the first time in many years because there was some global event that's gone on. Can't remember what that was. I expunged it from my memory, but we were able to get together. We met up in Rome because we are a team of Italians, Americans and Brits, and it was the Italians' turn to host the meeting. And I'd been talking about this new tool that I'd created and saying, you guys have heard me talk about this for 7 years. Well, it's finally done. It's working. And the meeting ended and we were literally sat outside the hotel waiting for our taxi to take us back to the airport when we got a notification from my system to say, hey, a couple of weeks ago, we looked at this bit of sky and that's what we found, i.e. nothing. And we just looked again a few hours ago and this was there. So I literally sat in the back of a taxi writing an announcement of this discovery in what's called an astronomer's telegram and writing a request to Swift to keep observing it. Because you see, we'd found this. So it took 4 hours. And most of that time was waiting for the satellite to go over the ground station and then getting the data down. It took about 3 minutes of data processing. When we had a look, what we found is this white circle is where the position is. So the X-rays were coming from somewhere in this white circle, which appears to be consistent with the middle of this galaxy. It's possibly, we think ruled this out, it's possibly consistent with a 2-year-old supernova as well. We had a bit of fun working out whether this could be caused by a 2-year-old supernova. Now, our initial thought, what I wrote in that announcement, what's called an ATEL, an astronomer's telegram, on the back of a taxi. By the way, don't try to write telegrams on computers in taxis. It made me feel really sick for about the next 4 hours, but whatever. We thought this was one of those tidal disruption events. It had all the hallmarks of it. It was about the right brightness. We could work out, we know the distance to this galaxy, so we could work out how bright it actually was. All of the X-rays were what we call soft X-rays. They were low energy X-rays, and it's right over the middle of a galaxy. So we said this is probably a tidal disruption event. And if we didn't have this real-time transient detector that I've built, that's where the story would have ended. What might have happened was maybe in a few years' time, someone like Rob would have been looking through a new Swift catalog and they'd have gone, oh, look at this. There was a sudden transient that turned on right over the center of a galaxy, and it was very soft. It was a tidal disruption event. That's probably been said about events like this. But we found it very quickly. So by the time I was on a flight back from Rome to the UK, Swift was observing this field again, and it carried on observing it for me almost every day, actually, ever since. And it turns out it is not a tidal disruption event. If it was a tidal disruption event, this is the light curve, it would have just gone something like that and would have disappeared. Instead, all the red points are times we've detected it, and all the grey points are times we didn't detect it, and we just know it's fainter than that upper limit. And basically what we found was it was on and it turned off quite abruptly. Then it turned back on again, then it turned off, and then it turned on again, and so on. It's not quite evenly sampled. We were only observing once a week around here. When it turned back on again, we went, oh, okay, we'll get more regular data. And then it did something a little bit weird, and actually it's then turned on again just recently. So what on earth is this? Well, we think this looks like something called a QPE. I mentioned QPEs briefly before. These were found in old XMM data. And a QPE stands for quasi-periodic eruption, and you're never going to guess what, but it's an eruption that's quasi-periodic. And what we mean by quasi-periodic is it's not got a strict period. It doesn't recur at exactly strict intervals, but there's a bit of variation. And the QPEs that have been seen by XMM tend to last for about 1,000 seconds, and they repeat every 8 hours or so. There's a bit of variation, but they're quite short. There's another type of event seen called periodic nuclear transients, and I'll let you guess what they are. But they have been found in the optical, and they do something similar. They seem to turn on, but they turn on for months and then turn off for a year and then turn on for months. What we've seen is lying somewhere in between the two. It's got the characteristics, especially of the QPE, but the timescales are all wrong. These outbursts are lasting about 10 days, and they're occurring roughly every 25 days. So well between the two. So it looks like, there we go, it looks like a QPE, but it's got a period of weeks. It's also the first one that's been found in real time, though. This is the first time we're able to say, go and get me more data now while it's happening. And what we think is going on, I'm afraid I don't have a nice snazzy movie for this. I should say this is the bit that's literally hot off the press and is kind of under wraps at the moment. I can tell you about it because it's my work. But it hasn't been published yet. It's under peer review, and I was literally reviewing the press release today, and the guys at NASA are doing as a nice, exciting movie, which I can't wait to see. But unfortunately, I don't have that to share. So assuming the peer reviewers accept it for publication, there'll be some splash on this in a few weeks or months, I expect. But what we think is happening is instead of that tidal disruption event where you've got a massive black hole, maybe 100 million times the mass of the sun, and you've got a star that's not actually in a fixed orbit around it. It just happens to stray too close and it gets shredded to pieces and swallowed up by the star. That's a normal tidal disruption event. What we think's happening here is you've got a star that actually is in an orbit around the black hole, but it's in a big, what we call eccentric, a really elongated one. And when it gets at its closest point, it's not close enough to be torn to shreds. It's just close enough to have a bit of its material ripped off and swallowed up by the black hole. So these first QPEs that were found in XMM that had periods of hours, they thought this is a white dwarf, which is what our sun will end its life as, around a kind of low mass black hole. Why I say low mass, I mean like, 10,000 times the mass of the sun. But as supermassive black holes go, that's pretty wussy. Then you have these periodic nuclear transients, and their stars, a bit like our sun, probably being disrupted by a proper supermassive black hole, like 100 million times the mass of the sun. So what we noticed straight away to start with is our system appears to, I should have put this picture back up, our system appears to lie in the middle in terms of its timescales. And when you go and speak to some clever people who understand the theory of this, and big shout out to Chris Nixon, who was 2 offices up from me and has now moved to Leeds, where he decided to run away. I don't take any personal responsibility for that, honest. So I'm inheriting his office, so I don't mind. But anyway, Chris ran the numbers on this, and it turns out that this event has all the hallmarks also of being a repeated partial tidal disruption. But not only does its time scale lie between these 2 other classes that have been found, but its physical characteristics do as well. We think that this is a sun-like star being periodically disrupted by a low mass, i.e. 10,000 solar masses, black hole. So it's a missing link that really joins up these 2 fields. This is why we're very excited about this. To give you an idea of scales, because space is big, as Douglas Adams famously pointed out, every time this sun-like star passes close to the black hole, every time we get one of these outbursts, we reckon it's ripping off that star about 3 Earth masses worth of material. So three Earths worth of stuff is being yanked off every time it goes around and getting hot and glowing in X-rays. So I'm very, very excited about this. I mean, it's actually a little personal story of, the effort that goes into what you often see in science is you get the press releases and you get the exciting result when you see, the end product. But it's taken 7 years of graft, sweat, an awful lot of swearing, and an awful lot of tea, in order to be able to produce the tools to do this. But it also raises a whole lot of questions as well. We turned this system on the 1st of April. On the 20th of June, we found this. How many more things are we going to find? How much more is out there to discover? And Swift is 18 years old. And in the last, middle of last year, it found this new object. later last year, it found a gamma ray burst so bright we reckon it's a 1 in 1,000 year occurrence. So Swift can do an awful lot of stuff. It can study gamma ray bursts. It can find fantastic bright things. It can find stars being ripped apart by black holes. I didn't even mention this. We found the first electromagnetic counterpart to a high energy neutrino. I just didn't have time to fit that in. We find these brand new events that are going off. So yeah, Swift rocks, and it's fantastic, the science that you can keep doing even 18 years in flight. So thank you very much for paying your taxes. Thank you very much for paying my salary. But I hope that what I've convinced you is that it's money well spent. I will stop there. Thank you very much.